Welcome to the Deep Dive, your shortcut to being well-informed. Now, if you follow the energy sector at all, solar photovoltaics, PV, they're absolutely essential these days.
Oh, definitely. The International Energy Agency even calls solar PV the new king of electricity
The
sources.
new king, right. And what's really crucial is that this energy transition, it's not just happening out in huge utility scale farms, it's happening right on your roof.
Exactly. We're talking about prosumers.
Prosumers, yeah, that's households, businesses, putting up rooftop solar, using it themselves, maybe feeding some back to the grid.
And their role is just massive. Some estimates suggest these prosumers could make up, 15% to almost 40% of all installed PV capacity globally by 2050?
Oh, no, up to 39%. That's staggering. But here's the thing. Those big forecasts often use, well, idealized numbers, don't they?
They often do, based on perfect conditions.
So the big question we need to tackle today is, what's the actual real-world performance gap for rooftop solar? How much power are we really losing just because a panel is on your specific roof instead of in a perfect field?
That's the core issue.
And understanding that real-world constraint, that's the focus of our deep dive today. We're pulling all our insights from one key source. It's titled Assessing Yield Disparities: Anticipated versus Optimal Rooftop Photovoltaic Systems and Implications for Prosumer Viability.
And that title really lays out our mission, doesn't it? This study, it aims to quantify what we call the anticipated yield loss.
Mm,
So comparing the actual expected performance of real-world rooftop systems, the anticipated yield, against, well, a theoretical benchmark,
sure shiz.
which is the yield you'd get from an optimally performing, perfectly modeled ground-mounted system like those big solar farms.
Okay.
We need to figure out how big that difference is, and maybe more importantly, how these real-world losses impact the economics for you, the prosumer.
Right, let's unpack that, starting with why this is even a problem, the modeling gap. You mentioned ground-mounted plants, solar farms. Modeling their output seems, well, relatively straightforward.
It is, comparatively. You can pick a good spot, tilt the panels just right, minimal obstacles. You generally get a clean, predictable output profile.
But rooftops?
Rooftops are, let's say, the Wild West of solar siting. You're putting panels where the building is, not necessarily where the sun is best.
So every roof is different. Different slope, different direction, trees nearby, chimneys.
Precisely. It makes it incredibly challenging to create a general yield profile for rooftop systems. Every single installation is almost a unique case.
And yet, the big energy models, the ones planning our energy future, they sometimes gloss over this.
Yeah, it's interesting. Even major models like Energy Plan or Times, they often just aggregate PV resources or use simplified, often overly optimistic assumptions for rooftop PV. They don't always capture this variability sufficiently.
Despite rooftop PV being such a huge part of the future mix, as you said.
Exactly.
So if they're not fully modeling the messy reality, what's the default benchmark they often fall back on?
They often use what's called the optimal yield. That's the theoretical maximum you could get. It's calculated assuming those perfect conditions, optimally tilted, fixed, ground-mounted systems. That becomes the benchmark.
But is that really a fair comparison? Apples and oranges, a purpose-built solar farm versus panels squeezed onto a suburban roof.
Well, it's not a fair comparison for predicting real-world output, and that's really the core point of this study. Using that perfect benchmark for actual rooftop installations is, well, fundamentally flawed. We need to account for the reality. And the difference, as this study quantifies it, is significant. And importantly, it varies a lot depending on the size of the rooftop system.
Okay, this is where the numbers come in. The study looked at the yield losses for different types of prosumers, right? Compared to that optimal baseline.
Yes, they broke it down into three main classes based on system size.
Let's start with the smallest, the ones most listeners might have. Residential systems.
Right. These are typically defined as systems of 25 kilowatt peak or kilowatt or smaller.
Okay, quick clarification. Kilowatt peak. That's basically the system's maximum power rating under ideal lab conditions.
Exactly. Standard test conditions. It gives you the theoretical peak capacity. So residential is up to 25 kilowatt.
Got it. Thanks. So these home systems, what kind of performance hit are we talking about?
Globally, the study estimates these smaller residential systems face an average 18% annual yield loss compared to that perfect optimal yield.
18%. That sounds like a lot.
It is substantial. And remember, that's just the global average. It varies quite a bit by region.
Like how much?
Well, they cited Denmark, for example, showing a deviation, a loss of 31%.
Whoa, 31%. Nearly a third of the potential power just not generated because it's on a real roof in Denmark.
Pretty much loss due to real-world conditions. That dramatically changes the economics, doesn't it?
Absolutely. An 18% average loss, potentially over 30% in some places. That residential segment seems particularly vulnerable to these real-world issues.
It is by far the most. But interestingly, as the systems get bigger, they tend to perform closer to the ideal.
Okay, so what about the next size up? Commercial systems, like panels on an office building or a supermarket.
For those, the study found a much smaller loss, an average of 7% annual yield loss.
Okay, 7% better. And the really big ones, industrial systems, massive warehouse roofs, factories.
They performed best relative to the ideal, only a 4% annual yield loss on average for industrial systems.
Wow. So 18% for homes, 7% for commercial, 4% for industrial. That's a huge difference. Residential systems are losing energy at more than 4 times the rate of industrial ones.
That's right.
We absolutely have to dig into why. What makes that 18% residential loss so much worse? Where is all that energy going?
This is really the fascinating part, the aha moment of the research, I think. The study breaks down that 18% into 3 main levels of loss. It paints a very clear picture.
Okay, level 1.
First is the environmental level.
Yeah.
This is basically about the sunlight actually hitting the panel surface. 2 main factors here. First, non-optimal orientation. Your roof probably doesn't face the absolute perfect direction, right? Or have the perfect tilt angle towards the equator.
Yeah, you work with the roof you have.
Exactly. So globally, that accounts for about 2% yield loss on average, just from not being perfectly aimed.
Okay, 2%. What else at the environmental level?
The bigger environmental factor is obstacles and shading. This is huge. Think nearby buildings, trees, chimneys, even parts of the roof itself casting shadows.
Right, the shadow from my neighbor's maple tree.
Precisely. The study estimates this causes a significant 7.5% loss of incoming irradiation on average for residential. It's very site-specific, of course, but shadows are a major energy killer.
Okay, so 2% for orientation, 7.5% for shading. That's nearly 10% loss right there, just from where the panel sits and what's around it.
We're already halfway to the 18%.
What's next? What happens at the panel itself?
That brings us to the cell and module level.
Yeah.
And the main issue here is actually heat, or rather cooling.
How so?
Well, think about ground-mounted systems. Air can circulate freely all around them, keeping them cooler. But rooftop panels are often mounted flush, or very close, to the roof surface.
Trapping heat underneath.
Exactly.
Yeah.
Less ventilation means higher operating temperatures for the solar cells, and hotter cells are less efficient. This effect contributes about 2.5% yield loss globally.
Okay, so add 2.5% for heat, or we're at 12% loss so far. 2 plus 7.5 plus 2.5.
Around that, yeah. Now, for the final piece, the system level. This relates to the electrical design and configuration. And here we find the single biggest factor that really separates residential from the others.
What is it?
It's related to how the panels are wired together in strings.
Mm-hmm.
Residential systems, being smaller, usually have only a few strings of panels connected in series. Now, the problem is, if just one panel in that string gets significantly shaded, completely blocked, say its resistance shoots up. And in many standard setups, that can drastically reduce or even stop the power production for the entire string it's connected to.
Wow, so one bad apple spoils the whole bunch, electrically speaking.
Kind of, yeah. Because there are so few strings in total on a small residential system, this effect is magnified. The study attributes a whopping 7.5% yield loss to this factor. Few strings, total module shading impact.
Another 7.5% just from that string design vulnerability.
Primarily from that, yes. There are other minor system losses too, like slight inefficiencies in power tracking or inverter sizing, maybe another couple percent combined. But that string shading effect is the dominant system level issue for small installations.
So let's recap the residential 18% loss, 2% from orientation, 7.5% from shading obstacles, 2.5% from heat due to poor ventilation, and another big 7.5% from the system's vulnerability to single-panel shading in a string.
That adds up. It really shows its combination of where you put it, what's around it, and how the small system itself is designed electrically.
That 7.5% string issue seems like a killer specifically for small systems. Does that problem just sort of fade away for the commercial and industrial systems, the ones only losing 7% and 4%?
It dramatically reduces, yes. And that's mostly down to scale and flexibility.
How so?
Well, think about commercial and industrial buildings. They often have large, flat roofs. This gives installers much more freedom.
Ah, so they can optimize the setup better.
Right. At the environmental level, orientation loss drops way down to just 1% because they can often use mounting structures to get a better tilt and direction, even on a flat roof.
Makes sense.
And obstacle shading becomes much less of an issue, too. Industrial sites are often in open areas, fewer tall trees or buildings right next door, so that loss drops to only 2% for commercial and just 1% for industrial.
So they start with a much better location, effectively. Less clutter.
Generally, yes.
Ah,
And critically, that system-level string problem, it almost disappears. Because larger systems inherently need many, many more strings of panels to handle the higher capacity. So if one panel and one string gets shaded, it only affects a tiny fraction of the total system's output.
the impact is diluted.
Exactly. That catastrophic system-level loss plummets from 7.5% in residential down to about 2% for commercial and only 1% for industrial. Their sheer size provides resilience against those localized shading problems.
Okay, that breakdown completely explains the 18%, 7%, and 4% figures. It's about location, shading, heat, and crucially, electrical design resilience that comes with scale.
Precisely.
Now we understand the why. Let's get to the so what for you, the listener, the prosumer. How does this real-world performance gap actually affect the decision to go solar and the cost?
Right, the financial implication.
The study used a model, the Eluti prosumi model, you said, to see how people would react.
Yes, a linear optimization model.
Yeah.
It looked at how these yield losses would change the optimal system design, things like how much solar PV capacity you'd install, how much battery storage, and the overall cost.
And they looked at the cost using a metric called ATCE, annualized total cost of energy.
That's right, annualized total cost of energy, ATCE.
Can you quickly explain what that means in simple terms?
Sure. Think of ATCE as spreading the entire lifetime cost of your solar and battery system, buying the panels, the inverter, the battery, installation, maintenance, everything over its whole lifespan, and averaging it out to a yearly cost.
Okay.
It essentially tells you the levelized cost of the energy you generate yourself. It lets you compare the cost of your own solar energy versus just buying everything from the grid.
Got it. So how does that 18% residential yield loss affect what people install and ultimately that ATCE number?
Well, the model showed a clear adaptation strategy. People tend to compensate for lower yield by simply installing more panels over installation.
Makes intuitive sense. If each panel produces less, you buy more panels.
Exactly. Especially in sunny regions with good economics, the model predicted that by 2050, prosumers would install up to 20% more solar PV capacity than they would have needed if they were getting that perfect optimal yield.
20% more panels, just to make up for the real-world losses. What about batteries? Do they install bigger batteries too?
That's where it gets a bit more complex. The reaction for battery capacity was non-uniform across the world, meaning it wasn't a simple install bigger batteries everywhere. By 2050, the model showed places like North America, Europe, and Eurasia actually tending to reduce their battery capacity compared to the optimal yield scenario.
Reduce. Why?
It's a complex optimization. Batteries are still quite expensive. The model seems to suggest that in some regions, given the lower yield from the panels, it becomes more cost-effective to slightly oversize the solar array, that 20% increase, and rely a bit more on the grid when needed, rather than investing in a very large battery to store lower amounts of generated energy.
So it's a trade-off between more panels, battery cost, and grid reliance.
Exactly. Other regions, meanwhile, saw battery capacity stay about the same or increase slightly. It depends heavily on local factors like sunshine, grid electricity prices, and technology costs assumed for 2050.
Okay, interesting nuance there. But the big one, the overall cost, that ATCE.
That increases pretty much across the board because you're fundamentally buying more hardware, those extra panels, to get the same amount of useful energy.
How much does it increase?
For residential prosumers, looking out to 2040 and 2050, the ATCE increases by up to 21% in almost all the sunny regions analyzed.
Wow, up to 21% more expensive over the system's lifetime.
Yes. The global average increase was around 16% compared to what the cost would have been, assuming perfect optimal yield.
So that 18% average yield loss translates roughly into a 16% average increase in the lifetime cost of the energy you generate.
That's a good way to summarize the bottom line impact. It's a significant penalty for residential systems operating in the real world versus the idealized models.
It really underscores the need for realistic modeling.
Absolutely. But here's the crucial positive takeaway from the study. Despite these losses and cost increases, even with the 18% yield loss and the resulting 16-21% cost increase, installing a residential solar PV prosumer system is still projected to be more economically favorable than relying entirely on grid electricity in the long term, looking at the 2050 scenario.
So even with the haircut, solar still wins out financially.
In most regions analyzed for the future, yes. The falling costs of solar technology are expected to be so significant that they can absorb this performance gap and still provide cheaper energy than the grid alternative by mid-century.
That's incredibly important. It means rooftop solar remains viable, even essential, but we just need to be honest about the real numbers.
Precisely. And it highlights why using dedicated, realistic modeling that accounts for these anticipated losses is so critical for planning. If policymakers or utilities rely on the optimal yield figures, they will drastically underestimate the amount of rooftop capacity needed and the true system costs involved,
You'd end up planning for way less solar than you actually need people to install.
leading to potential shortfalls in meeting renewable energy goals.
Okay, so summarizing the big picture, rooftop solar is vital, no question. But its real-world performance, especially for homeowners, is significantly lower. That 18% average hit is real.
It is.
And this requires adapting, mainly by installing more capacity, which increases the cost. But thankfully, future solar economics look strong enough to handle it.
That's the main conclusion. The economics are resilient enough to overcome the physics, essentially. But it does lead to a final thought.
Go on.
We identified that the single biggest chunk of the specifically residential loss, that's 7.5%, came from the system-level issue, the vulnerability of strings to single-panel shading.
Right, the Achilles heel of small systems.
So, a provocative question for you, the listener, to consider. This study modeled systems based on typical current technology assumptions. But what if technology evolves to specifically tackle that 7.5% loss?
You mean things like microinverters or power optimizers?
Exactly. Technologies like microinverters, which handle the power output of each panel individually. If one panel is shaded, it doesn't drag down the whole string. The study didn't assume widespread use of these, as they add cost up front.
But if they became standard or much cheaper?
If you could effectively eliminate that 7.5% system-level loss with smarter electronics, how much more powerful, how much more financially attractive could residential solar become? Could we close a significant part of that 18% gap purely through technological innovation at the system level?
That's a great question. It shifts focus from just accepting the loss to actively finding ways to mitigate the biggest parts of it through better tech.
Making distributed solar even more potent.
A fascinating thought to end on. We've been deep diving into the findings from assessing yield disparities, anticipated versus optimal rooftop photovoltaic systems, and implications for prosumer viability. Thanks for joining us for this deep dive.